This lecture focuses on what digital evidence is, how courts and investigators treat it, and why it is uniquely difficult to handle. Lecture 1 defined the field. Now you learn the object of study digital evidence and the practical obstacles that make collection and analysis hard. Lab will practice imaging, hashing, and metadata inspection on Kali Linux. The session moves from definition and admissibility through sources and categories into major challenges, then mathematical models like integrity, Bayes, timestamp, and finally Kali Linux labs. Digital evidence is information of probative value stored or transmitted in binary form that may be relied upon in proceeding, ISO and cache framing. It includes files, emails, databases, logs, memory dumps, packet capture files, mobile application data, cloud object, metadata, timestamp, and geolocation. For example, in a theft case, a global positioning system (GPS) point from a phone photograph PNG EXI format data, a building access card log, and a closed circuit television CCTV clip are all digital evidence if they help prove presence at a location. Digital evidence is latent, that is, it needs tools. It's fragile, that is, easily changed. It's volatile, like random access memory RAM or a network, yet duplicable as perfect bit copies, unlike blood. It is time sensitive, like clocks, total time to live, log rotation, and highly contextual implications. A forensically sound copy can be examined while the original is sealed. For example, investigated image a hard drive, seal the original in an evidence bag, and an autopsy only on the hash verified image so accidentally delete during analysis never touch the except. Evidence must be relevant, authentic, reliable, and obtained lawfully. Chain of custody document who collected, transferred, stored, and analyzed item break, reduce weights, or risk exclusion. For example, if a universal serial bus USB device passes from officer A to analyst B with no signed handover, and later the hash differ from accusation, defense counsel can argue the exhibit may have been tampered with even if the content looks incrementing. The categories that should be taken into consideration in digital evidence include persistent storage like hard drive, solid state drive SSD, universal senior bus USB, volatile memory, network PCAP file, packet capturing file, NetFlow file, application data like email, chat, browser, cloud remote sources, and device sensors global positioning system, GPS or Internet of Things, IoT devices. Now, for example, a stalking investigation might use phone GPS like sensors, WhatsApp database like application, and the router dynamic host configuration protocol DSCP log uh, together for analysis. Paper era is usually considered as the best evidence rules evolved, but in digital practice, accept properly authenticated bit identical copies verified by hash. Standard workflow includes write blockers, secure hash algorithms like SHA-256, analyze the image, preserving original. For example, a code accept a DD image of a server disk when the examiner testifies about write blocking, hashing, tool versions, and that analysis never mount the original evidence drive read write. Digital forensic faces six interconnected challenges that investigators routinely encounter in the field. Volatility. An order of volatility. demand that evidence be captured in a precise sequence starting with RAM, then running processes, and finally disk storage. Since powered off systems lose live memory instantaneously, and even a single micro-order step can corrupt volatile artifacts like network connections or decrypted file caches. Volume and velocity overwhelm labs as modern devices generate terabytes of data at machine speed, making it impossible to manually inspect every file, registry entry, or log within reasonable timeframes. Encryption locks evidence behind keys that may be unrecoverable if strong passphrase, hardware security modules, or full disk encryption like BitLocker or FileVault are deployed without escrow. Anti-forensic actively sabotage investigations through log wiping, timestamp manipulation, steganography, or rootkit that hide attacker presence and erode the chain of custody. Cloud and jurisdictions fragment evidence across geographically dispersed SaaS platform, service as a service platform, email tenants, and virtual server often in countries with strict data sovereignty laws or no mutual legal resistant treaties, forcing investigators to navigate subopinion delays and provider-specific logging gaps. Timeskew introduces critical error when system clocks network timestamp and log files across distributed environment are not synchronized, causing even reconstruction to misalign and corrupting timeline analysis. For example, a corporate laptop used by a department employee is found powered on but locked. The investigator must first image its live RAM volatility before the battery dies, only to discover the 2 terabyte SSD contains an encrypted Outlook cache encryption synchronized to a Microsoft 365 tenant in Ireland cloud jurisdictions. While the user has executed a script to wipe Windows, even logs and alter file times anti-forensics, all while the laptop clock was 12 minutes behind the domain controller, and the cloud audit logs use UTC plus 0 time skew, forcing the examiner to correlate these inconsistent timelines while processing millions of emails under a tricky legal hold deadline. That means in terms of volume or velocity. The first challenge is volatility. Order of volatilities covers in request for comments RFC 3227 and National Institute of Standard and Technology NIST, which prioritizes register cache, then routing, address resolution protocol, process tables, random access memory, temporary file system, then disk and archives. Delaying loss evidence. Live acquisition can change state, so competence and documentation matter. For example, for a running malware sample believed to hold encryption key in RAM, capturing memory with a vetted tool before pulling the power cable may be the only way to obtain those keys. Next challenge is volume and scale. Terabyte disk and multi-device cases make full manual review impossible. TriEdge uses indexes, timelines, and known file filters such as National Software Reference Library, that is also known as NSRL. If n files and review rate is r files per hour, time is n by r unless filtering shrinks n. For example, hashing all operating system files against the NSRL may eliminate 80% of a window image as known good, letting analysts focus on user folder and odd executables. The next challenge is encryption. Full disk encryption with uh, BitLocker, Linux Unified Key Setup looks or file vault, end-to-end encryption, messaging, and container block dead box access. Live random access memory may hold keys. Cloud-side legal processes may be alternative. For example, a seized MacBook with file vault shows only an encrypted blob when image cold. If lawfully obtained credential or a live memory image container key is available, the same disk become readable and that decision may be documented. The next challenge is anti-forensics. Adversary wipe media, timestamp modified, assessed and created times, hide data in Slack space or steganography, deleted logs or pack malware. Detection often relies on inconsistency across artifacts like master file table versus log file versus prefetch. For example, a file standard information um, timestamp claim creation in 2010, but prefect and log file shows first execution yesterday, suggesting timestamping rather than a decade old innocent file. The next challenge is cloud and jurisdictions. Evidence may sit outside the investigator country. Mutual legal assistance treaty processes provide application programming interfaces, APIs, and shared tenancy complicate snapshots. Key question: who controls data? Which law applies? And which law prove authenticity? For example, a local fraud rate case need Gmail headers and login internet protocol addresses. Investigate cannot simply image Google servers but must use lawful process to obtain mailbox content and audit logs from the provider. Term of service and provider policies also shape what can be requested. Let's move to the some of the important concept before covering the lab session. First concept is integrity verification model. Integrity holds if and only if hash of E is equal to hash of I for evidence bitstream E and image I, using a strong hash such as secure hash algorithm 256-bit SHA 256 per Federal Information Processing Standard FIPS guidance. Digits belong in custody forms and should be recomputed before analysis sessions. For example, Monday execution hash is A3F1, means starting with A3F1 and so on. Wednesday before autopsy, the examiner rehash and get A3F1 and so on. Again, documenting the working image remain unchanged over storage. The next concept is Bayesian thinking for evidence weight. Posterior odds equal likelihood ratio times prior odds. Bayesian theorem framing for evidence weights. This framing prevents treating one artifact as absolute proof. For example, finding a malware hash on a person's computer raises the probability of the evidence given compromise relative to the probability given a clean system. But if the hash also appear in the legitimate software package, shared library region or bundle tool, the likelihood ratio is weaker than unique command and control domain match would be. Next concept is timestamp uncertainty. Observed time equals true event time plus clock skew plus error. Flush delays time zone mistakes. Always record time zone, network time protocol status and skew when imaging live system. For example, a laptop set to local time without daylight saving time correction should will show email sent at 2 p.m. while the mail server coordinator universal time UTC log shows 9:30 a.m. without documenting the offset, for example, plus 5:30, and the skew, the cyber trail appear inconsistent when it is merely misaligned. The next one is avalanche effect, hash sensitivity. Flipping one input bit changes about half the hash output bits. Hamming distance near n by 2. Any undetected write invalidates prior digest. Hence, write blockers, for example, mounting an evidence universal serial bus USB device read write for just a quick look may update last access times. The secure hash algorithm 256-bit SHA-256 of the device content no longer matches the sealed acquisition record, creating a custody nightmare. Lab goals. Lab create a forensic style imaging with DD, DC3DD, DCFLDD tools. Verify secure hash algorithm 256 SHA-256. Extract exchangeable image file format EXIF. Metadata with EXIF tool. And inspect header with XXD or file. For example, you produce slash temp slash evidence copy dot image, a matching hash log, and a EXIF dump showing global positioning system coordinate from a sample photo used as practice evidence. In Lab 1 Safe Image Demo, you can build a small loop mounted fourth extended file system ext4 image, place a node file, unmount, then copy with DC3DD hash SHA-256 or DD plus SHA-256 sum, confirming source and copy digest match. For example, even a 50 megabyte practice image train the same discipline used on a 1 terabyte disk hash. Log path never works on the original file if you can avoid it. Let's start the experiment. The first step is to create a 50 MB blank file filled with zeros. This is the command which will create a fake image file, and the file name is evidence123.image created in the temporary folder. So a file has been created. The second step is to format the file as an ext4 file system. Why we are doing formatting for ext4? Because it simulates a real disk. ext is a standard Linux file system, and majority of the tools like a Topsy, SaluteKit, FTK Imager, they support ext4, and it make the exercise real. So let's execute the command. The command to perform this action is this. It's asking for the root password. So you did, and you will get output like this. The next point is to create a mount point and mount the image. This is to make the raw disk image behave like a real one and attach drive so that you can perform read write files inside it. So the first command is this. This command is creating an empty directory to act as an entry point mount point where the file system will appear, and the -p flag ensure no error if directory is already existing. The next command is this. This command attaches the image file to a loop device, a virtual block device that tricks the operating system into treating the file as if it is were on a physical disk plug-in. So both commands are executing. The next step is to create a test file inside the mounted image. So this step is optional, but if you want, you can create it. So you can see I'm creating a test file node.txt in the mounted environment, and this file will be having text secret note. The next command is unmount command. This command. Now sudo unmount slash mount slash ev forces a kernel to flush all cache writes from the RAM to the actual image file. Until you unmount, Linux may hold data in memory buffer, so that node.txt you created might not physically exist inside evidence 12 image file yet. Unmounting ensures the file system is fully synchronized and consistent, which is critical before you hash or copy it. Without this step, your hash 256 hash would reflect as an incomplete image, breaking chain of custody integrity. The next step is to create an image of the original file. The original file was evidence123.img. Now we are copying it into evidence123 underscore copy.img. This is a typical style of forensics. Rather than working on the original file, we create a copy of it and we work over the copy. So a copy has been created. The final step in this experimentation is to compare the hash value of the original image and its copy image. So you can see here using SHA-256 when you are computing the hash value of the original image and the copy image is same. So that means now we can work on the copy image and can investigate further. The next experimentation is to collect the metadata and header information. So in this experimentation, we take a sample image, JPG image, and try to extract the information using EXIF tool. So EXIF tool reveals, create, modify global positioning system, camera, software fields, and many more information. Followed by XXD shows magic byte logic photographic expert group JPG, which is usually start with FFD8FF, file confirm type, stress the metadata can be forged and must be corroborated. That means if you have the data with you, the metadata with you, that metadata is not could not be a trustworthy metadata, that as it can be forged as well. So for example, a photo claim GPS inside a bank at a midnight, but the photo tower logs and building closes circuit television, the CCTV plays the device elsewhere. So metadata is changed. So metadata alone must not overrule stronger independent evidence. So we are going to follow these steps mentioned in this slide to analyze how we can collect the metadata information. So let's start with the experimentation step. So the simplest one is take any image and use the EXIF tool to get the detailed information. Metadata information. So this is the complete metadata which you can see is giving the GPS informations and many more informations. So all of this information we have to analyze. So in this lecture we are covering just an overview of this execution. In later lectures or recordings, I'll go through this tool in details and will perform more experimentation. So this was the one EXIF file, and then you can, if you want a specific information like create modify GPS camera software, you can use this command to get the intended information. So you'll get what is the camera, what is the software used, who modified it, at what date it modified, created, and GPS details. So all this information you can get using this command. Now you can also get here file information. So you can get use the file command as well to get more information. So these are the important tools, the commands which you can use to collect information or metadata about an image. Then let's move to the next experiment, which is non-file filtering idea. Here you can run SHA-256 sum on files in a directory, sort and find duplicate, digest conceptually like NSRL non-good, non-bad matching to shrink volume. For example, to different named files, report.pdf and reportfinal.pdf, sharing one secure hash algorithm, SHA-256 are bit identical output. So only one need deep content review for duplicate analysis. Let's understand this with uh, practical. So here we are creating a folder called hash lab and moving to this folder for practice. The folder has been created. Now we need to download some images to perform this experiment. So I'll be downloading some images using wget command. So here I'm using wget command to download first image and naming it as photo1.jpg. So the first image has been downloaded successfully. Now I will download the second image and naming it as photo2.jpg. So the second image is downloaded successfully as well. The next command is to create a copy of uh, duplicate copy of um, the image. So you can create two copies of photo 1. So the two copies for photo 1 image has been created. The next step is to compute hash of all files in this folder. So the hash has been created and the hash values are stored in /temp/hashes.txt file. You can see the hash value using the cat command. So all file hash values you can see here. Using this command, you can see those who are having the unique hash values. So the photo1.jpg evidence 1_a.jpg and copy of photo1.jpg. All three is having the same hash value. So you need not to investigate all of these files. So you can investigate any one of these files to get the metadata, header and other informations. So this way you can save your time on analyzing all of the files. You can analyze only those files which are having unique hash value. So I'm repeating the lab ethics. So the never image production system without authorization. So use right blockers for real media. Treat EXIF global positioning system as sensitive personally identify informations. So for example, publishing a classroom screenshot of EXIF tool output that include the student home coordinates would be an ethics failure even if the technical command was correct. So these are the important references which you can refer for more statistical learning and experimentation. So this is the second list of important references for the standards which you can refer to understand the forensic concepts. We'll be covering these concepts in future as well. Thank you very much.